So Sophie is, maybe I introduce her to the audience. She's a master's student at the HdM, and she's presenting a work that has been accepted as a paper at the
electronic imaging.
ISNT.
ISNT, yeah.
ISNT, that was the Zungenbrecher. And well, I think it's time.
Yeah.
Have fun.
To start. Okay, so good evening everyone, and thank you all for being here. Today I got the opportunity to present to you my work on the paper with the title Evaluating the Angular Resolution of a Simulated Light Field Display in regards to three-dimensionality, motion parallax and viewing experience. But since this title might seem quite long, I will lead you all into the topic and explain what we did exactly, so don't worry. By now you probably have all seen digital advertisements like these, where huge LED walls show a kind of digital room extension into the back. So here we can see a whale like inside of a building. And as we can see, this looks amazing from this perspective, but this changes as we move around in space and take a look at it from a different point of view. We will then face major perspective issues. For example, we can now don't see the head of the whale anymore and it just looks weird. And these issues can't be solved with traditional 2D LED walls or displays. So I will give you a quick introduction into display technologies to take us all to the same starting point. So as we all know, conventional displays only display one image. So if I look at my screen right here, I only see one image, and if I move around, I see the same image all the time. But there exist multi-view displays that are capable of showing more than just one source image, and they cast the different images into different directions in space, as you can see on the right. And if we would fill the views of the display with different views of the same scene, we could simulate a motion parallax. Motion parallax means that I gain different information about a scene as I move around. For example, if I move around here, I can see you now I can't see you, and so on. So that's motion parallax. And if we would use a stereoscopic 3D display, we could also show a stereo parallax, which means I see different images on each eye. But in this particular study we only used a conventional 2D display and only simulated the motion parallax. So no real 3D, we only simulated the motion parallax. So a light field display shows also several views of a scene. And for our study, we created 7 stimuli with a wide range of different angular resolutions. But what is a different angular resolution and what does it affect in the displayed image? Here we can see 2 examples with different angular resolutions. The top one is high with 60 degree per view, and the bottom one is lower with only 10 degree per view. And the angular resolution is calculated by the ratio of the display's field of view, so in which direction it shows an image in space, divided by the number of displayed views, as you can see in the calculations over there. And on the right, we can see the views displayed in a top-down view, and we notice that the more views we have, the closer they are together. So in the top one, we see that we only have 3 views, and they are far apart from each other. But in the bottom image, they are very close to each other, and therefore they get more similar to each other. So we can see that we have visible vertical slices in the top image. We see clearly red, and then orange, and then yellow. While in the bottom one, we have more of a gradient. So yeah, it's just smoother. And that's because the displayed views become more similar to each other. So the same effect of this also applies to light field displays with lots of displayed views. The more views we display, the less vertical artifacts are noticeable. So the bottom one is the one we are striving for. And in relation to the angular resolution, there were 3 factors we wanted to survey. So the first one is, how does it affect the effect of three-dimensionality? Does the motion parallax help to recognize the object's shape? And does it even improve the viewing pleasantness, or is it disturbing or annoying? So with that said, the final questions we wanted to answer is, how three-dimensional does the object appear? Does the object position-dependent appearance of the object help to recognize its shape? And how pleasant is the viewing experience overall? Here we can see the final stimulus of the study. So what we can see here is a conventional 2D display. And I thought I would show it right away so we can all imagine what we are working towards with the stuff I tell you. And what happens here is that the conventional 2D display we can see here, it's just like a standard display, simulates a light field display. And depending on the person's position in the room, so in this example, me holding my smartphone and filming, each pixel shows a specific predefined color. And if I change my position while moving around in front of it, the colors change. And that's why we can see a changing image based on a changing position. So back to display technology. Most light field displays are built using subpixels, and every pixel has a specific number of subpixels. In this image we can see 3, so blue, yellow and red. And we also have a lens in front of it that leads the light of the subpixels into specific directions in space. We can see here that the blue subpixel will be seen between 0 and 60 degrees, and as soon as we move a bit more to the right, we will immediately see the yellow subpixel. And it's the same with the red one. And to prevent that from happening, we applied a specific light emission pattern to the subpixels with a linear fall-off. And what we have now is that if we stand at 30 degrees viewing angle onto the display, we see 100% blue. If we move to 60 degrees, we would see 50% blue, 50% yellow, and at 90 we would see full yellow. So we have a gradient between the images, so it's no harsh edge, but it's more like a blending between the images. Yeah, and at the same time we will not lose luminance, because if we add all the light intensities up, we are all the time at 100% except for the borders, but we just ignore them. So with that information we can now actually create the simulation. And we go quickly back to the stimulus. We now understand that we are working with subpixels and their viewing angle dependent visibility. So viewing angle means the angle I'm viewing onto the monitor. And the next step is to actually calculate these visibilities of each subpixel to display the final output image we can see on the screen. And this is done by tracking the person's position. We actually can see the the black box right underneath the monitor and also in the picture over there, and that tracks my position and 3 coordinates in space, and that's used for calculating the right output colors. So when we obtain the position of the observer, we can calculate the viewing angle onto the screen pixels, and therefore we can calculate the subpixel intensity maps you can see down there. It's basically just alpha maps, technically speaking. And later on, these get combined with the source images that we will render in Cine4D. I will get to that in just a second. And these source images contain the color values for each and every subpixel at every point on the display. And adding all of these together, just applying alpha map to source image and then adding it all up will give us the final output image. And yeah, the adding up and the calculation of the alpha maps will happen in Touch Designer in OpenGL. And I will first talk about the calculation of the alpha maps, and then we will go on to the rendering of the source images. So to generate the alpha maps, we first have to find out the exact viewing angle, as I said, from the user onto each and every display pixel. We only did a horizontal simulation because we normally don't change in height when we move around, and we only, our head stays the same height, so we only did it for horizontal angles. And like I said, we track the position of the person in the room, and through a rather simple trinomial calculation we can obtain the viewing angle delta. We only have to do one case differentiation. You can see it when the person moves on the left side, that we calculate 180 degrees minus the arcus tangents, and that's our viewing angle delta onto the pixel. And in the bottom image we can see the example of one display row with 3 subpixels. So these are the subpixels, and these are the intensities for the row. And for example, at the 3rd pixel we have 100% blue, then nothing yellow, nothing red. And as we go over there, in the end we have 100% red, and in between we have some yellow, some blue, some red. Yeah, and that's how we can calculate the alpha maps I just showed you in the graphic before that. In the next step we need to render the source images, and that's done in Cine4D. The stimuli show a minimalist object consisting out of basic geometric shape. You can see it in the right corner down there. And it's interwaved so that occlusions occur. that you can move around it and always discover new things about the shape. And moreover, it's shifted by 45 degrees to provoke lots of diagonal lines, because these diagonal lines will be very visible in the vertical stripy artifacts I just explained earlier, because they will offset, and yeah, it just looks very bad, and we wanted to provoke that. And the object is rendered in Cinema 4D with a parallel render cam, and any horizontal compression that occurs when we look at it from the side is corrected by an in-camera distortion map to prevent loss of resolution. The stimuli were evaluated in a study amongst 32 participants, of which 18 were male and 14 were female, and the average age was 24.9 years. And it was a quantitative survey to determine a mean opinion score that ranges from 1 bad to 5 excellent. And we determined the mean opinion score for the 3 questions on 7 stimuli, so 21 questions per person. And the evaluated numbers of views were 1, so basically a standard display, 45, 90, 180, 360, 720, and 1440 views, all on a field of view of 180 degrees. So if we take 180 divided by these numbers, we get the angular resolution, but we will work with these numbers. So the subjects enter a room with a masked area in which they can move freely, but they are instructed to move from each outer corner you can see on the ground at least once per stimulus. And the simulated light field display is installed at eye level, and it has a size of 32 inches. And in the beginning there is a short training phase in which the 45 and the 1440 views stimuli are shown to guide as reference. I will just show them to you right away. And if we take a look at the left one, we can see something weird going on. We see that pictures kind of blend weirdly together, and on the right we can see the lowest angular resolution, so the most views presented, and we see nothing, like no artifacts. Yeah, and after the short training phase, the other 7 stimuli are presented in random order. And now we can go to the results. So the first question examines a subjective rating on how real the presented object behaves in comparison to real-world surroundings. So it is neither about the quality of rendering nor the effectiveness of the simulated motion parallax, but on the overall appearance and feeling of the object and the setup. And we can immediately see that the ratings rise with a higher number of views, so that's good. And it's almost a linear rise in MOS in a logarithmic rise of views, so notice that at the bottom it doubles, but in the y-axis we have a linear scale. And that means that doubling the presented views always results in a similar rise. For example, if we put plus 45 views, we get the same rise as if we put plus 180 views, for example, so that's an interesting fact. And the largest increase in MOS can be found between 180 and 360 views, while the smallest increase is located between the uppermost ones. And at the same time, the second largest standard deviation is at 720 views, and the lowest one right next to it at 1040 views. So this indicates that probants were more confident in giving the lowest angular resolution a good rating compared to the evaluation of 720 views. For the next question, the subject should focus on the motion parallax and evaluate by standing still versus moving in front of the stimulus if they gain more information about the object's shape. So again, the ratings show a nearly linear rise in MOS between 45 and 720 views, and we can see a plateau and even a slight decline forming between the uppermost 2 stimuli. And this indicates that the participants might not have recognized the difference between these two because they rated it the same. But that's weird because objectively the higher number of views offers less artifacts and therefore more information about the shape, but the ratings were the same, so probably the probants didn't even see a difference between them. This gets interesting in the next question, so remember that. And also the 3 stimuli with the highest angular resolution have a higher standard deviation than the 3 with the lowest angular resolution. And this could indicate that probants found it easier to quantify their experience for a lower angular resolution, so they were more confident in saying, yes, that's good. And on the last question, the the question is subjective and emotional as well, since even an artifact-free image is worthless when it's disturbing or annoying to look at it. So that's also an important question. And the one view rating stands out since participants agreed in rating it decently with 3.16 point on average. And as we remember, if we would see the 45 views example I just showed you in the beginning, it's not really pleasant, so that makes sense. So the one view rating is greater than the 45, 90 and 180 views rating. And nonetheless, participants' rating fluctuated a lot, which can be seen in the highest standard deviation. We also have a large increase in MOS, again, between 180 and 360 views. So this step kind of seems to enhance the experience a lot. And also the lowest angular resolution, again, gets the highest MOS and also the smallest standard deviation. So participants agree that this is the most pleasant stimulus. But when comparing this observation to the ratings of the other two I just showed you and said, yeah, remember that, it's important, it seems quite kind of odd, because in the other two questions, they rated, or most of the time they rated the 720 and 1440 views almost the same, or even the lowest angular resolution a bit less. But here they clearly kind of prefer the lowest angular resolution. So do they recognize a difference or not? Do they see a difference or do they just feel a difference? They don't seem to gain more information, but they still kind of like the lowest angular resolution the best. So yeah, that's a question I asked myself a lot. So what are the conclusions we can draw? Overall, we can say that the MOS rises with a higher number of views. And we see that the effect of three-dimensionality and the recognition of shape is better with the light field display than with the one-view standard monitor setup. And in contrast to that, one view tops 3 out of 6 light field display stimuli in regards to the viewing pleasantness. We have the plateau at the first two questions, but regarding the viewing pleasantness, no such plateau is seen. We have still a rise. We don't know how much it will rise with even lower angular resolutions. And also, all the ratings had a significant standard deviation. And the possible reasons for that, you can see here. It could be due to a number of reasons, some of them being the small sample size of only 32 participants, the length and setup of the training phase, maybe people couldn't really quantify the experience, the varying familiarity with the technology, that's oftentimes a problem with light fields, that people don't really understand what they are looking at and like what's happening. The different movement patterns of the subjects in space, some moved around a lot or very fast, some just moved their head a bit and stuff like that. And maybe we also had some biases, for example, in the shape of the shown object. So maybe if we show a real-life scene or a different object, the ratings would be different. Also, the choice of the emission pattern, that it blends into each other rather than having sharp edges, could like improve the ratings a bit because it doesn't look that annoying. And also maybe we have a learning effect in terms of the object shape, especially when it comes to the questions of how well you recognize the shape. Maybe we have to make it a bit more challenging. And these biases can't be verified nor ruled out. And for future studies, it would be interesting to examine even lower angular resolutions, so to present even more views. To lower the step size between the examined resolutions to really see if we have a plateau or if it's still rising, and also maybe use a better tracking system to reduce the latency. Yeah, that's it. Thank you all for listening and for coming, and feel free to ask anything.
Yeah, thank you very much.
You're welcome.
Very interesting talk about this perspective views. So when do you expect, is there an application on the wall?
Do you mean when, like in time? Yeah, I hope soon. Like I can really imagine it for like event installations or to freak people out, like what's going on here. Yeah. And I have all, like there exist light field displays like in this size and in this size, and they really look amazing. So yeah, I hope they will get cheaper.
I think it's everybody who has seen some of these in life is really
Yeah, it's like, what's going on?
To see an object in front. But still, there is a huge technological barrier between.
Yeah.
The question is real-time rendering is an option. Yeah. And displays coming from a game engine.
Yeah. Actually, I've seen some real-time rendering, but I don't know in which software they did it, so probably something game engine-like. Yeah.
Yeah. Are there questions from the audience?
I'm trying to understand the view number like 1430, like you rendered from 1440 times from different angles.
Yeah,
right?
yeah.
But how can you combine it with the alpha maps? Like you always said, it's only 3 alpha.
No, it's the same amount.
Yeah, that makes sense.
Yeah. It's per source image you have one alpha map, yeah.
Yeah, I understand.
Yeah.
But only can track 1 people each time. Right?
Yeah, yeah. Sadly.
Yeah, it's only this one display.
Yeah.
It's one display.
It's only one output.
So, no micro lens and nothing.
No.
I wonder if you've tested or investigated larger displays and whether or not the results of your evaluation show different results.
Yeah, they will show different results, but I haven't tested it.
Rather that the acceptance is lower then, or the bigger the display gets? Or?
Yeah, I think so. I haven't really wrapped my head around that, but also with the scene depth, like what you show, like this is as deep as the monitor is in width, but this also changes as we tried for deeper scenes.
I don't know, too many
questions.
Yeah.
I wanted to ask actually the same that Volker asked, but also if you tried the looking glass, because it's available in 32 inches.
I've seen it.
I actually saw it in I think 50 inches once, which was very astonishing, and for me it worked really well actually to have a look at it. But of course it's very expensive, and I think it just has 100 steps over 56 degrees, right?
Yeah, something like that,
something like that. So you actually do see like when you move from step to step. But
and another weird thing with the looking glass is that you only have like a sharp area in the middle, and when the object comes out or goes back, it gets more sharp. Yeah. But I can recommend to look at the 32-inch version of the looking glass.
Okay.
Yeah.
So if I understand correctly, with the applied method, it's not possible to do the vertical change, right?
You can do it, but you have to... Yeah, you can actually do it, but you have to calculate twice or fourth as much, because you have 2 dimensions. So if you have 10 views here, you will then have 100 views of you presented in both directions.
Because the larger the screen gets, you don't have to move up and down with that, but just moving towards.
Yeah, we only did it to save render power. Yeah. Yeah.
Have you seen the use explore like the use case? For example, I think in The Mandalorian they did it to shoot live action movies and have real lighting. Basically, I think they did camera tracking, and so they basically got a background which moved around with the camera, and also the lighting on the actors was basically more realistic.
Yeah.
Was
yeah, it's like similar, but not like this is brute forced. We have the fixed views, and then I track and I just grab the views. But what they did is they rendered it in real time in the game engine, so it's a bit different. But yeah, it looks the same. But in the end, this should work for like an unlimited amount of people. But the one you mentioned only works for 1 camera. So yeah, that's the cool thing about that one. Yeah.
So is the lowest resolution you tested, would that be already enough to have a different image of each eye every time?
Like in this, not, because it's not a stereoscopic display.
That's clear, but if it would be
I would say yes, but it also depends like how far you stand away from the display. But you can calculate it. I can send it to you later. Yeah.
Okay. But I still want to ask.
Yeah.
Go ahead.
If for the small display, actually, you don't need the gray, the alpha plane, like a gray from white to gray. It's only for the big display, right?
What do you mean with big and small?
So for the small, you don't have different. Well, I'm standing here. For the small, it's the angle difference to the both sides of this display is actually really small. So
yeah, as smaller the display gets, it doesn't really change. But even with this, like you stand 4 meters away, it's still different. Yeah.
Okay.
And like quite fast. So I tried it with like 8, 16, and 32, and even at 32, you have like 10 different images already on the screen at the same time.
Okay.
So it's
yeah.
Yeah.
In order to calculate if you would put the display above or below the subject, since it uses like another dimension, or would it?
Yeah, if we would simulate that, yes, but we didn't. Like it would be cubic? No, not cubic. Quadratic. Oh my god, the amount of render power.
Well, thank you very much again.